We have seen the stationary points and various other concepts in graphical behavior using calculus. We will now see point of inflection and what is point of inflection and why it is connected with calculus. To start with, let me take a curve something like this. By definition, we see that for this curve, you have a part where the graph is concave down and concave up. So the point where the concavity changes is called point of inflection. So it is somewhere here that I have, say I just cut the graph out here from this point to this, and then I get point of inflection. So this is where the concavity cuts. So here we get the point of inflection, and by definition it is nothing but the point where the concavity changes. So point of inflection is point on the curve where concavity changes is called point of inflection. Now there are different curves which have different points of inflections, which is also called inflection. This word sometimes is replaced with inflection. So let us see the different types of points of inflections which exist in the branch of mathematics. I first take the curve which I put above. So this is one of the case. Now the other shape which can be out here is this. So I will take the different shapes and see for each of them what the point of inflection would be. Now the third case is ever increasing with some flatness out there in the middle. Now this curve is something like ever decreasing with flatness in the middle. So these are the four types of shapes which exist in the branch of mathematics. So let us see how the point of inflection comes. So here it is concavity change from concave down to concave up. So this is what I have seen here, that this has become concave down, concave up from concave down. So here I get the point of inflection because I see that at this point the point of inflection or the concavity changes. If I see this third case, the case 1, case 2, case 3, case 4. If I see the case 3, I see that slightly at this point there is a concavity change where the graph moves downwards to upwards. It is downwards and then moving upwards. So similarly here, I get the point of inflection somewhere here where the graph tries to be from concave up slightly to concave down here. So these are the four cases which come with the point of inflection. So this being the point of inflection for the first curve, this being the point of inflection for the second curve, and this being the point of inflection for the third curve and for the fourth curve. Well, the biggest challenge now is how do you find exactly this point? How to find this point exactly. Now, why do I use the word exact? Because we may wrongly fall into the assumption that this may be the point of concavity change or this may be the point of concavity change. But why are we looking only at one specific point which makes us understand the point of inflection? You cannot have more than one inflection point for a curve, for one situation of a curve. So here I cannot have two inflection points or three inflection points. So I cannot call A, B, C as inflection points, but only B is the point of inflection. But why do we think so? Or how do we think we can exactly find these 4 points of inflections is what is the challenge in calculus. So let's get into this. So in general, calculus says that if you have a curve, something like that, let me take the case 1 out here, let me take more clearly out there. Okay, so in this case, I've taken a smooth, clear curve of the case 1 of the previous 4 cases. So in this case, we know that this is where the concavity changes. So let me assume this perfect point to be the point of inflection. So calculus says that if A is point of inflection, say if my point here is point of inflection, then the rule is that for this to be a point of inflection, I have to have f double dash of x is equal to 0. So why do you think f double dash x equal to 0 exclusively at the point of inflection is the biggest challenge out here? So my question is, why f double dash x is 0 at this point of inflection, and how? So let us see the why and how of this concept, which is very important and makes you understand in depth why point of inflection. So in this case, in order to understand the point of inflection, we need to understand the gradient of a tangent. So if I just draw a tangent at different points, I see that the tangent keeps decreasing with slope. It comes out there with certain points out here. So here the tangent at every point of the curve tries to come at certain stage. So it is quite difficult to draw the tangent here. So what I would be doing here is I will just take the tangent here at all points and so on and so forth, something like this. Okay, to some extent, I see that the slope of tangent here, for example, if I just take the slope of tangent, we all know that in calculus, gradient of a tangent to the curve is f dash x. So I'm looking at the slope, which is f dash x. So we see that as we go above, in this case, I see that the slope is reducing. So in this case, the gradient of tangent becomes less steeper in this case. If we can see that the more steepness is reduced and finally becomes flat. And it goes on and on to see that the steepness again is more here. Now at this point we see that again, interestingly, the steepness again increases. If I just look at this point, I just see to it that the steepness is increasing. So here the steepness, the gradient of tangent becomes less steeper, but after this point, the gradient of tangent suddenly tries to reverse the steepness. So the slope of tangent at this point, at this particular point, suddenly reverses its steepness. Now this important property makes a concavity change. So this is one specific property that suddenly reversing the tangent with its steepness is where the point of inflection occurs. That's why there is only one point of inflection for any curve where the steepness suddenly reverses, and at that special situation we call that as point of inflection. So we call exclusively this as point of inflection. Now let us see why it is f double dash x equal to 0. So we now come to the conclusion that there's only one point of inflection. There is only one point of inflection here. Now what makes f double dash x is equal to 0? Let us see that. Now as I told you that at this point, the gradient of a tangent reverses its steepness in the sense it is trying to change from, reverses in the sense trying to change from positive to negative or negative to positive, which can happen only when passing through 0 at that particular point. Positive, 0, negative, or negative, 0, positive is what makes here at this particular point where I have point of inflection with f double dash. We know that the gradient of tangent is f dash x, and the rate of change, this is nothing but the rate of change of gradient with respect to its x is nothing but d by dx of f dash x, because we know that the gradient of the tangent is f dash x. So the rate of change of gradient of tangent with respect to x, with respect to its x, is d by dx of f dash x, which is nothing but f double dash x. So point of inflection, the rule is, so for point of inflection, the rule is f double dash x equal to 0. Now there are two types of points of inflections. One is horizontal and non-horizontal, because in this case, if I draw a tangent, I just get a non-horizontal point of inflection. If I just draw a line out here, then I see that I get a non-horizontal point of inflection, something like this. So this is non-horizontal point of inflection. Now what is horizontal point of inflection? Non-horizontal point of inflection, because the tangent at that point is non-horizontal. Therefore here f dash x is not equal to 0. F dash x is 0 only when the tangent is parallel to x-axis or when the tangent is flat. So when the tangent is flat, we get f dash x equal to 0. If the tangent is not flat, or this, in this case I get f double dash not equal to 0. So let us revisit the previous case of the four cases. Okay, so in this case, I see that here, in this case, f double dash x equal to 0, f double dash x equal to 0, and I have here also f double dash x equal to 0 and f double dash x equal to 0, but I see the condition that here it is non-horizontal tangent, therefore f dash x is not equal to 0, and f dash x again here is non-horizontal, so not equal to 0, but I get a flat tangent out here and flat tangent out here. Therefore the special condition here is f dash x equal to 0 and f dash x equal to 0. So we get horizontal inflections or non-horizontal inflections connected with it, the four cases. So I have non-horizontal with f dash x not equal to 0, and each of the case inflection is because of f double dash x equal to 0, is how we see the two properties connected with stationary points and point of inflection. So this is how we understand the rule of point of inflection and why and how of f double dash x connected with point of inflection. Thank you.